Okay, what we're going to do in this chapter is really dig into limits and how they work and what they look like, and really start applying them to the different types of problems that you're going to see. And so the easiest way to do that is just to dive on in and talk about limits that we've seen 1,000 times before, and those limits are asymptotes. And we've talked about them, and we've looked at them, and we've graphed them, and we've put dotted lines where they should go, but here's what they really are. So the line y equals b is a horizontal asymptote of the graph of a function y equals f of x if either the limit as x approaches infinity of f of x equals b, or the limit as x approaches negative infinity of f of x equals b. In other words, as your graph grows really, really large or it goes really, really small, it approaches a specific number. So what we're going to do is use graphs and tables to find the horizontal asymptotes of the following two questions. And I'm going to minimize the notes just a little bit so that we can see the graphs here, and I'll show you a graph and table for each one. And so first off is x over the square root of x squared plus 1. We're going to look at this guy first, and you'll see him right now. And basically, we want to know about the horizontal asymptote of this guy. So as x gets really, 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 really big, what number are we approaching? And it looks like it starts to level off kind of. It's hard to tell, but if you look really close, our graph levels off somewhere around y equals 1. Okay, now it might not ever say 1 in the table of points, and it might not ever say 1 on the graph or look like it. It might look like it, maybe gets closer, maybe doesn't, but it's 1. And then if we go towards negative infinity, by the way, this is when x goes to positive infinity. And then when x goes towards negative infinity, then what we're going to notice is that the y values approach a different number, negative 1. And so that's a horizontal asymptote. This guy's got two of them. Kind of cool, I know. So anyway, that's what a horizontal asymptote does. You've seen it before. You've done it before. You just get to do it some more. All right. Switching gears now and throwing a trig function in there. We've got sine x over x. Now this is an interesting one for horizontal asymptote. Remember that you can't have 0 in the denominator. So if we graph this guy, remember that we're not interested in what happens at 0. We're interested in infinity, okay? And so we want to know that what happens with this graph as x approaches positive infinity. And what's going to happen is the sign is just going to bounce back and forth between 1 and negative 1. But the bottom, the denominator, is just growing exponentially. So where does this guy go? This guy's going to go to 0. And the same thing is going to happen when you go to negative infinity. When you've got x approaching negative infinity, and you can see it on the graph and in the table that I'm showing you right now, when x goes to negative infinity, this graph also goes to 0. So what does that mean? That means that for this problem, y equals 0 is a horizontal asymptote. Hey, now let's look at some more limits, and what we're going to do is check out the limits as x approaches infinity. So if you're looking at the screen right now and you're looking at those limit rules, something should be tickling in the back of your brain, because yes, we've seen all of these before, but we've just looked at those rules as we've approached a specific number. Well, now we're going to really dig into what happens as we go to infinity. This is going to be more discussion along the lines of what kind of asymptotes are we going to have. So let's try out these properties. As x goes to infinity, we can look at this as the sum of two different things. So we would have, for this particular guy, we would have that we would look at the limit as 5x over x plus sine x over x. We would look at this limit right here and see what was going on with that. And as the limit goes to infinity, hey, by the way, looky here, these x's cancel. So this guy's just going to be 5 plus, And then over here, remember we just looked at this one, sine x over x. That limit as it goes to infinity is going to be 0. And so using our properties, as x goes to infinity, we're going to see that we should get 5. And that is what the limit is as x goes into infinity. And I'll also, I have a graph showing right now as well that allows you to kind of get a good visualization on what this graph looks like as you go towards positive infinity. All right, we just took a really close look at how horizontal asymptotes work, what they look like as it moves to infinity. We use those limit properties. And in this example, we're going to actually check out vertical asymptotes as well, because those are also really important. And we're going to look at those asymptotes as we approach specific numbers from left and right. And so that's what the little plus and minus signs mean now under your limits. That just means that the plus sign means we're coming from the positive end of the number line, and the minus sign means we're coming from the negative end of the number line. And we're going to put those together, and we're going to see how these asymptotes look in limit form. It's really actually kind of neat. So we're going to define a vertical asymptote to be the line x equals a is a vertical asymptote of the graph of a function y equals f of x if either of these two limits exist. And so we've got both of these limits here written for us. Notice that this guy is going to come from the positive side of the number line. This guy is going to come from the negative side of the number line. And so that's kind of what we're looking for. Now, how about finding those vertical asymptotes? Well, sometimes it can be really hard to see, but what we have to do is we have to look at these guys in terms of those two specific limits. Now, where are we undefined right here? And the answer is we're undefined when x is 0. Okay, can't have 0 in the denominator. So what we need to do then is look at the limit as x approaches 0 from the left of 1 over x squared, and look at the limit as x approaches 0 from the right of 1 over x squared. And so when we do this, what's going to happen is we get really, really close to 0. We're undefined there. We can't have 0 as part of our answer. But when we get really, really close to 0 from the left-hand side, we'll notice that the numbers, we're getting really, really small numbers on the top. So 1 divided by a really, really, really small number is a really, really, really big one. And so we're going to discover that this limit, whoop, that's the wrong color. We're going to discover that this limit right here is going to go to positive infinity. And I've got a graph up for you to see so you can follow this graphically. Sometimes with vertical asymptotes, it's a lot easier to see graphically. The same thing is going to happen with the blue limit. And the reason they both go to positive infinity is because if you take a negative number and square it, it becomes positive. Okay? Now, let's look at the tangent. It's a little bit different. And so what we're going to do is look at the graph of a tangent. And when you look at this graph of tangent, you'll notice that it makes the same shape over and over and over again. And you might remember this from last year also. You might remember this shape. And so what happens is as we approach odd multiples of pi over 2, we're going to be undefined, okay? And so then what happens then is we just have to look at what's going on both sides of the odd multiples. So the limit that we would set up for this guy, it's going to look a little bit weird, but you can see it on the graph, and it's going to be something like this. When x approaches that odd multiple, we're going to let that equal a. All the multiples of pi over 2 equal a. When we approach a from the left of tan x, and the limit as we approach a from the right of tan x. And what you're going to see is that on one of these, we're going to go to negative infinity, which will happen to actually be the positive side. And then on one of these, we're going to go to positive infinity, which will be on the left-hand side. And so it's a toughie, and it's a lot easier to see when you look at it with sine and cosine, but we've got to get where we can understand how tangent works too. So here's a real quick introduction then on finding vertical asymptotes. Hey, every now and then, after you've done all the other asymptote stuff, sometimes it's just easier to look at end behavior in general of a function. And the end behavior of a function usually tends toward a specific asymptote, and sometimes on a slanted asymptote or what's called an end behavior asymptote. And those work for large values. And what we can do is take a very complicated, long drawn out polynomial, and we can just look at end behavior, because a lot of times with asymptotes and large values of infinity or whatever, we just need to know what's going on in the extreme locations, way big numbers or way small numbers. And so what we're going to do is look at a problem here and use an end behavior model to try and figure out, maybe what the limit is, or what's it going to, or can I show that these two things are the same for large numbers? So that's what we're going to do here. And I'll sum it up again. We can sometimes model the behavior of a complicated function by a simpler one that acts virtually the same way. Again, we're not interested in numbers that are small, close to zero. Okay, end behavior means large numbers. So we want to show that f and g are different values, are different for small values of x, but are similar for very large values. So let's look at our hint, which says that we should put f over g and look at a limit. So when I do that, I get this. And we're going to use some rules of fractions here that I hope you can remember. And if you can't, maybe after working this problem, we'll have jogged your memory. We did work a very uncomplicated, similar question earlier. But remember, we can separate everything onto the top over the bottom. So I would have 3x to the fourth over 3x to the fourth minus 2x cubed over 3x to the fourth plus 3x squared over 3x to the fourth minus 5x over 3x to the fourth plus 6 over 3x to the fourth. And so when we're working these problems out, we're trying to find these limits. Notice that a lot of these limits will reduce a little bit. For example, the first guy right here reduces all the way down to 1. The next guy, minus, reduces to 2 over x. The next guy reduces to 1 over x squared. The next guy reduces to 5 over 3x cubed. And the last guy reduces to 2 over x to the fourth. Okay, so then when we look at these things, what ends up happening is all of these values, they all tend towards 0, because the top now never changes and the bottom is growing larger. So anytime that happens, you're going to have a 0 for your limit. So if we put our limit question back on this guy as x approaches infinity, all of these go to 0. And that leaves me then with a 1. And so I've got this true statement right here. And so what that tells me then is that for very large values, not close to 0, but large values like millions, these two different functions are virtually the same. All right, so now we want to find an end behavior model. And we're going to just be given a couple of polynomials here, and we want to dig through these polynomials and do a little bit of math and find an end behavior. It's really pretty simple. And if you go back and look at the previous example that we were just talking about, the end behavior model actually was the leading terms reduced down, and that gave us an answer of 1. And so that's a big deal, because if we have a polynomial divided by another polynomial, we can look at what that end behavior is going to look like based on what those leading terms are. So let's go ahead and look at these two examples that we've got right here and see if we can't figure out what the end behavior models are. First off, the most important thing is we need to know what our leading terms are. And on the left, it's 2x to the fifth over 3x squared. On the right, it's 2x cubed divided by 5x cubed. So let's just go back to the left side. Our end behavior model then is going to resemble this. 2x to the fifth divided by 3x squared. Just reduce that down as far as you can. Well, 2/3 will not reduce. It's as reduced as it's going to get. But 5 and 2 do reduce. If I've got 2x's on the bottom and 5x's on the top, I can reduce those down to a cube. So my end behavior model on the left is going to be 2/3 x cubed. Well, what about on the right? On the right, we're going to have 2x cubed over 5x cubed. And again, when we look for things that can factor out, the 2/5 doesn't change. It's going to stay 2/5. But the x cubed divided by x cubed factors out, and so we end up with an end behavior model of 2/5. In other words, a horizontal line at y equals 2/5. And this is just one kind of way that you can find an end behavior model. This is really the easiest one, and in fact, it's a really good way to determine if you have a horizontal asymptote or not. As we've discovered with the red one, we've got a horizontal asymptote, and so this is a really easy way to see those as well.